Before we start talking about significance tests for a difference of proportions, I want to remind you of a few things about significance tests for proportions when we had one sample. We started out with the null hypothesis where the population parameter equals some value, whether it's 0.5, 0.2, whatever it was, and the alternative was either a greater than, a less than, or a not equal to. And our z-test statistic was p hat minus p over the square root of p1 minus p over n. And if you remember, we got this value, the p in our formula for standard deviation, from the null hypothesis, from the population claim. We didn't use p hat at all when we made our standard deviation of our statistic. So keep that in mind as we do the difference of proportions significance test, because our standard deviation formula is going to look a little bit different than it does for one proportion. Let's read through this example together. According to a website, Black and Hispanic females are underrepresented in STEM programs compared to non-STEM programs. So they did a test, or they took a poll to see if this is true for the whole student population at this certain university. So they took a random sample, that'll come into play later, of 300 STEM students and found that 12 were Black or Hispanic. A separate random sample of 500 non-STEM students had 75 Black and Hispanic females. So the parameter or the parameters of interest, let's let P1 be the proportion of Black and Hispanic females in STEM, and then let P2 be the proportion of Black and Hispanic females in a non-STEM field. The statistic that we care about is the difference in this proportions. We're trying to see if there's a difference, or they're trying to see if they are underrepresented. So what they mean by underrepresented right here is that there would be fewer STEM females than non-STEM females. So our hypothesis would be that the null hypothesis is P1 minus P2 equals 0. There is no difference between the proportion of females in STEM and the proportion of females in non-STEM. And we suspect, or this website suspects, that they're underrepresented in STEM, so that means P1 minus P2 would be less than 0, implying that P2 was greater than P1. And so we're going to use these statistics, P hat 1 minus P hat 2. We care about the difference in the proportions. And we can go ahead and calculate that so we have that information for later use. So P hat 1 is 12 out of 300, and P hat 2 was 75 out of 500. And when you calculate that, you get negative 0.11. So just by looking at our statistic that we calculated, there's some evidence to suspect that this website is correct and that it holds true for this university. But we're going to do a significance test to see if we have convincing evidence. Right now we have some evidence to support this. Let's use 0.05 as our significance level. And the name of our procedure, now we're going to do a 2-sample z-test for a difference of proportions. You don't have to write for a difference of proportions if you don't want to, but it just helps so you can remember its proportions. It's a z-test. We're going to use z, I have p hat, all of those things. So let's check that the conditions are met. Both of them were random samples. I highlighted that up in the passage. So both random samples. Normal, you have to show that N1 times P hat 1, which 12 over 300 was 0.04, that's greater than or equal to 10. 300 times 0.96, that's greater than or equal to 10. 500 times 75 over 500 is 0.15, greater than or equal to 10, and 500 times 0.85 is greater than or equal to 10. So all of those are met. so we can meet the normal condition. And the third condition was independence. Both were independent samples because 300 is less than or equal to 10% of all the females, the Black and Hispanic females on campus. And then 500 is less than or equal to 10% of all the females on campus, the Black and Hispanic females. The mean of our sampling distribution, and so the mean that we're going to use, mean of p hat 1 minus p hat 2, is just p1 minus p2, which is going to be 0 from our null hypothesis. We got that from our null hypothesis. Now, our standard deviation, though, is a little bit tricky because if you remember from when we did one sample, we got our p hat, or we got the p for our standard deviation from the null hypothesis. But now our null hypothesis value is 0, so we can't use that number. So what we have to do is calculate the pooled or the combined p hat that we're going to use. So we can't use the p1 minus p2 equals 0 because then our standard deviation will be 0. So we're going to calculate something new. It's called the combined p hat, and it's where you have the total of the numerators over the total of all the samples. So that ends up being 0.109. So we're going to use our pooled or combined proportion instead of using our null hypothesis value to get the standard deviation. So you always need to use this. This is not on the formula sheet. You have to know to combine these proportions. So our standard deviation then is going to be, now we're going to use our combined proportion here over N1 plus our combined proportion again over N2. So let's plug that in. We've got the square root of 0.109 times 1 minus 0.109 over our first sample plus 0.109 times 1 minus 0.109 over our second sample. And when you type that into your calculator, you get 0.0228. So that's our standard deviation. And we've got, so we have our mean, we have our standard deviation. The next step to find our p-value. So we need a test statistic to get a p-value. And the general formula for test statistic, which is provided on your formula sheet, is statistic minus parameter over standard deviation of the statistic, which is what we just calculated. So for this case, we have our p hat 1 minus p hat 2 minus our null hypothesis, which is 0, or the mean of our population, which is 0, over that whole big square root that we just had. And I'm just going to say that. I don't want to write it again that small. So let's plug in all of our values that we have. We have p hat 1 minus p hat 2. That was from the very top of your page, negative 0.11 minus 0 over the standard deviation we just got, 0.0228. And we end up with a test statistic of negative 4.83 when you type that into your calculator. And so what that means is if the difference is 0, or in other words, if there is no difference, we're trying to figure out the probability that we get a difference of negative 0.11. So here's negative 4.83. So if there is no difference, what is the probability of getting a difference of negative 0.11 or more? and you might recognize that wording from the interpretation of a p-value. So if there is no difference between these proportions, what's the probability of getting a difference of negative 0.11 or more? So that's what we're calculating our p-value. So remember, our test statistic was right here, negative 4.83, and to get a p-value for z, it is normal CDF from negative infinity to negative 4.8301. We get a p-value of basically 0. You'll end up with scientific notation in your calculator. So we can use that p-value now to write a conclusion. Compare your p-value to alpha. So since it's less than alpha, we're going to reject the null hypothesis, which means there is convincing evidence for the alternative hypothesis. So remember, we were trying to see if the proportion of women in STEM was lower than the proportion of women in non-STEM. So that was our alternative. And so since we rejected the null hypothesis, there's convincing evidence that the proportion of Black and Hispanic females in STEM fields or STEM majors is in fact lower than the proportion in non-STEM. So let's summarize some of the main ideas from the example we just did. The null hypothesis is going to be P1 minus P2 equals 0, meaning there is no difference. No difference. And the alternative hypothesis will either be P1 minus P2 is greater than, less than, or not equal to 0. So greater than, less than, or not equal to 0 would mean one's higher, one's lower, or they're the same, or they're not the same. You will also, we introduced a new topic, the combined proportion. You have to use this to get our standard deviation of the statistic. So our combined proportion, p hat combined, is our first x1, our second x2, n1 plus n2. And where you get those numbers is p hat 1 is x1 over n1, and p hat 2 is x2 over n2. So we have to get a combined proportion, and you need this to get the standard deviation of the statistic. You need this for the z-test statistic. We also used the mean of a sampling distribution of a difference of proportions. And we are going to use the standard deviation of our statistic is going to be the square root of our combined proportion instead of using the individual p hats. Right there. And our test statistic is p hat 1 minus p hat 2 minus 0, because that's your null hypothesis, over that square root that we just wrote right there. So let's do one more example using this information. So we're going to study the long-term effects of a preschool program for poor children. So they designed an experiment. They recruited 123 children who had never attended preschool. So this isn't a random sample of participants, but they did randomly assign them to two groups. So that would include the randomness. So we can't make this inference about the entire population of all preschoolers. Our population is 123 children. So technically, the sample size is just 62 and 61, not 123. So we're using a little bit of wiggle room here. So they recruited 123 children. You're making a lot of assumptions here since they recruited them. And so they randomly assigned them 62 would attend preschool and 61 would not go to preschool. And over a 10-year period, the 38 children in the preschool group and 48 in the control group needed social services later in life. So like maybe they had learning differences or behavior problems, things like that. They needed social services from the state. So we're trying to see if this provides convincing evidence that preschool reduces the later need for social services in children like the ones in the study. So let's start by stating everything we know. Let's define our variables. Let's let P1 be the proportion of preschool attendees, preschool children, needing social services, and P2 is going to be the proportion of preschool students, of non-preschool students needing social services. So our null hypothesis would be that there's no difference. Going to preschool has no influence on whether or not you would need social services. And they're suspecting that people who go to preschool will not need social services. So they're thinking that P1 is going to be lower than P2. So P1 minus P2 is less than 0. And if you want to put off to the side, P1 would be lower than P2. Fewer children who go to preschool will need social services later in life. Let's say everything else we have. P hat 1 is going to be 38 out of 62, which is 0.61. And P hat 2 is 49 out of 61, which is 0.80. And we can go ahead and get the difference. P hat 1 minus P hat 2 is going to be negative 0.19. We know since we're doing a significance test, we're going to need our combined proportion. So you might as well get that while you're at it. 38 plus 49 over 62 plus 61 is 0.71. That's what we're going to use for our test statistic formula. And they don't say an alpha, so let's use 0.05. So let's check if the conditions are met. Like I said, it wasn't necessarily a random sample, but we did randomly assign them to groups, so each of the samples is random. Each group is random. 62 times 0.61 is greater than or equal to 10. 62 times 0.39 is greater than or equal to 10. 61 times 0.8 is greater than or equal to 10, and 61 times 0.2 is greater than or equal to 10. Now, if you think about the 10% rule, that means that your samples would be independent, but what you have to think about when you do experiments is each outcome independent of another outcome? In other words, does one child's experience in preschool affect the learning of another child's experience in preschool? So what you have to think about is this is an experiment, then you don't have to meet the 10% rule for an experiment. So an experiment, then you would say it's an experiment, so each subject is independent. This is new, a new condition here for doing experiments. Now we're starting to do experiments, so each subject is independent. That's okay. So let's calculate our test statistic here. Z equals P hat 1 minus P hat 2 minus 0 over the standard deviation of the statistic plus P hat C 1 minus P hat C over N2. Let's plug in our values. Negative 0.19 minus 0 over the square root 0.71 times 0.29 over 62 plus 0.71 times 0.29 over 61. And when you type all that in the calculator, you get negative 2.32. So we have stated all our given information. We have defined our variables. We stated the conditions and we checked them. We found our test statistic. Next thing we have is our p-value. So let's draw a curve to get our p-value. So assuming there is no difference between the two proportions, we want to calculate the probability that our difference is negative 0.19 or higher. So our p-value is going to be normal CDF, negative infinity, negative 2.3201, and when you type that in the calculator, you get 0.01. We can write our conclusion. 0.01 is less than 0.05, so we're going to reject the null hypothesis, which means there is convincing evidence that if you go to preschool, you'll have a less need for social services later in life. So we've concluded that you are less likely to need social services if you are a child who attended preschool. So based on this conclusion, did we make a type 1 or a type 2 error? Since we rejected the null hypothesis, we have potential for a type 1 error. So we have a type 1 error because we rejected the null hypothesis. So the error we could have made is that we reject the null hypothesis, we conclude that going to preschool will reduce the need for social services, so we start something like the Georgia Pre-K program where we encourage all children to go to pre-K or to go to preschool, and so that might use more resources up front, and then in the end it didn't make them less likely to need social services, so the state is spending money on sending kids to preschool, and we're still spending the same amount of money on social services. So the goal would be, okay, let's spend the money to send them to preschool, and then we're not paying for the social services later on in their life. But we made the type 1 error where we made that decision, but we actually were wrong. It didn't reduce the need for social services. So now we're paying money to send kids to preschool, and we're paying money for their social services later in life. So the consequence, always think of a consequence even if they don't ask you one, because it's important to practice this for when they do ask you for a consequence. So you conclude that preschool reduces the social services needs later in life, but it actually doesn't. So you're spending money on preschool and social services instead of just preschool.